Question here of multi-reaction equilibria. Quite often we'll find that we have more than a single reaction going on at a given time. And as an example, let's assume we've got these species A, B, C, D, E in our system, and subject to the two reactions, A plus 2B goes to C plus D, and 2A plus D goes to 2B. Let's assume ideal gas behavior for this reaction, for these two reactions. Then the relevant information that we have to describe the system that we're dealing with, of course, is the extensive reaction. I have to put subscripts on the Xi's now to indicate which reaction I'm talking about. So I have a Xi1 and a Xi2. And then if I can determine what the standard free energy changes are and the standard enthalpies of the reactions are from the relevant formation reactions for all of the species that are involved in the reactions, I can ultimately develop an expression for the equilibrium constant. The usual thing that we've done is to assume that these delta H's are constant with temperature, so we will get a rather simple relationship for log K as equal to some constant minus another constant over the absolute temperature. So we'll assume that these things are obtainable from the information that I've indicated here. The main issue I want to talk about is the stoichiometric description of the system. We can write down the expression for K1 here, and this would be, there's too many subscripts to write, but I'm talking about just K expressed in the usual way in terms of the activities. And if I break it down just according to the stoichiometry of the reaction, then it looks like this. And I can, if I've assumed ideal gas behavior, I can factor those out into Y each time I've got the pressure there, and I'll end up with pressure with an exponent equal to the stoichiometric number for the reaction. And for reaction number 1, we see that what that is minus 1 minus 2 plus 3 plus 1, so it ends up being equal to 1. So nu is equal, for this one, is equal to 1. And for a second reaction, similarly, I can decompose it here in terms of the continued product here of the activities raised to their respective stoichiometric coefficient powers. And then that can, because I've got an ideal gas system, I can break that down into the same expression here in terms of Y's. And then I need P with an exponent equal to the stoichiometric number for reaction 2, which is going to be minus 2 minus 1 plus 2, or in this case, that's going to be minus 1. So I've indicated that here. So let's assume that that information is given to us. That is, I've given the reactions here and the temperature of interest and the pressure of interest, so I have everything I need to know to solve stoichiometrically for what the composition of the system would be here, subject to both of these reactions at the same time. So here are reactions, and I've got a Xi1 and a Xi2. And out of these I want to construct expressions for all of the mole fractions that are involved. So YA, of course, is NA over N, and we've seen earlier how to write that out if I have a multi-reaction case. The initial value, then I have to then account for what happens to A in both of the two reactions. So I see I've got, if I write in the stoichiometric coefficients here, in each case I end up with an expression that looks like this for YA. And if you've got that figured out, then it's an easy matter to write down the same set of expressions for the other mole fractions that are present in the system. So if I can get this thing to work, then we can see those. We've got YB, C, D, and E all written out in the same way. Everyone clear on how we do this? So next what I want to do is write out expressions for the equilibrium constants, the Ky values, for both of these two reactions. And they look like this. And here you notice I've got the P's in here with their respective powers equal to the exponents given by the stoichiometric numbers for the reactions. So assuming that I have these are then just numbers at the particular temperature of interest. Then I should have a pair of equations that I could solve simultaneously for these two extensive reactions, Xi1 and Xi2. That can be confusing. If I plot those up, I may get a number of possible solutions. So we need to consider carefully the allowable ranges for these extensive reactions, Xi1 and Xi2. and that means looking at the limiting reactants. So here's our initial inventory. I hadn't specified it before, but let's say that we're given a mole apiece of A, B, C, D, and D, but nothing of E present initially. So for reaction 1, I can identify the limiting reactant, and I just look at it here. I've got a mole of both of the reactants, but I have a higher stoichiometric coefficient here for component B, so it's evident right off the bat that the limiting reactant, I think, is B. And the amount, the stoichiometric amount of that limiting reactant that I have, of course, is going to be that initial number of moles divided by the absolute value here for the stoichiometric coefficient, so it's 1/2. So that's the maximum value that Xi1 can take on. Well, we notice that D and C are both present. We have a mole apiece of them. So that means that the reverse reaction is also a possibility. So I need to consider that and look at what the limiting reactant would be for the reaction running in reverse. And the stoichiometric, the limiting reactant for the reverse reaction would be C, and I would have a maximum possible value of that of 1/3. Everyone see that? And that would tell me that the minimum value here of Xi1 is -1/3. So what I'm looking at is the range, allowable range for Xi1 to be -1/3 to 1/2, plus 1/2. So we need to do the same thing for the second reaction and look at what the range of values that we allow for Xi2. The limiting reactant to Xi2 is going to be A. I think that's evident. And its stoichiometric amount is 1/2. And there is no E present initially, so that means that the reverse reaction can't run. And that tells me that since that can't run, then we have allowable range for Xi2 running from 0 to 1/2. So as complicated as these expressions that I've had for Xi1 and Xi2, both of the two equations that I need to solve simultaneously are relationships between Xi1 and Xi2. And they're usually so complicated that we aren't able to explicitly write those out. But we have the equations nevertheless expressing those relationships. And I could write them down here and then plot them in the allowable range for Xi1 and Xi2 and get something that looks like this. And in the allowable range that I've shown here, Xi1 from -1/3 to plus 1/2, and Xi2 going from 0 to 1/2, I'm only going to find one root. And actually, a convenient way to solve these types of systems is to do it graphically. And it's fairly simple to do in Mathematica here, using the contour plot function. So a contour plot, I don't know if you're familiar with that, you could just write down the two functions and the allowable ranges for each of the variables. Here I've written it as x and y, and just as an illustration, I've shown the simultaneous solution of this x squared plus 1 over y plus x equals 3. Second equation is square root of y minus x equals 3. And I put an allowable range here, -1 to 1 for x and 1 to 3 for y. And that gives me only a single root here that I can find. And I can, of course, home in on that and get it to any degree of accuracy I might want. Now it turns out that if you plotted these and let the range be larger, you'd find many roots for these. So that's the mechanics of it, so I hope that helps with being able to take care of the homework problem that involves simultaneous reactions. Next important issue that I want to discuss here is what I refer to as equilibrium conversion temperature diagrams. Now what we should realize is that the bottom line of interest, as I stated here, in any reaction is the amount of conversion that can be achieved. And conversion actually is achievable is going to be limited by the kinetics, but what we're determining here is the thermodynamic limits on that conversion, and we refer to that as the equilibrium conversion. Well, we need to define what we mean by it. Fractional conversion here, and I'm going to use a capital X to designate it, is the fraction of the limiting reactant which is consumed. Now we should note here that many times we don't have just a single limiting reactant. I could have more than a single reactant with the same stoichiometric amount. So either one could count as a limiting reactant. And if I have them all in stoichiometric proportions, then any one of the reactants can be regarded as a limiting reactant. So it's important to realize this definition. And let's recall that the limiting reactant is the one in least stoichiometric amount. And from the definition that I've given up here, we can calculate what the conversion is. It said it's the fraction of the limiting reactant consumed. So the amount consumed here, of course, is the initial value of the mole number for the limiting reactant minus whatever we had at that instant of interest where I want to determine what X is, divided by the initial amount of limiting reactant. Right? And if I write down the expression for this numerator, then of course that's just going to be minus the stoichiometric coefficient times xi. And I'm using the subscript L here to refer to limiting reactant. So everyone see this? Now X will run from just 0 to 1. The most we can do is not consume any of it or consume all of it. So it can run from 0 to 1, and we see here that it is directly related to xi. And if we cleverly choose our basis by setting the mole number here numerically equal to the stoichiometric coefficient, then this thing is just going to become 1, and I get X equals I. Right? So if I have in a reaction a stoichiometric coefficient here, let's say -2, then I will choose as my basis an initial value here of -2 moles. And then everything else is proportioned accordingly. And if I do that, which I'm going to do from now on, then xi is equal to X. And so now xi runs from 0 to 1 in this case. But what we're looking at here is this conversion. Everyone clear on this? Now the dependence of this conversion X on temperature at constant pressure is what I'm interested in. This will give us the equilibrium conversion temperature relationship or curve. Now again, let's go back and assume we have an ideal gas system, and every time I'm using the examples here with ideal gases, but you know how to fix that if you have to, because I've shown you yesterday how to handle non-ideality. But if I have an ideal gas system, then the equilibrium constant here, and I've just indicated a subscript T here to suggest that it's at temperature of interest T, is equal to the Ky times the pressure of the system raised to an exponent, which is the stoichiometric number for the reaction. And I can write here xi is the same as X. And let's invert this around, because what I'm interested in expressing stoichiometrically is this Ky as a function of X. And that's equal to our equilibrium constant here in terms of activities, times the pressure now with an exponent equal to minus the stoichiometric number for the reaction. So at a given pressure, this thing is just a function of temperature. But over here, I've got the Ky is just a function of conversion X. So this is the equation I want to take a look at. I just indicated that. So I take logs of both sides of this equation. I get log of Kyx is equal to log Kt minus nu log P. This is now, as soon as I put in the appropriate thermodynamic descriptions here, I can evaluate this whole thing in a functional form. Looks like this. Now what we note is that as X goes up, Ky goes up, or vice versa. So I'll notice that as Ky goes up here, that would go up if delta H, with temperature, if delta H is in fact negative, and vice versa. So right away we should get an idea that will allow us to write qualitatively valid looking equations for the conversion as a function of temperature. Let's take a look at that. So if we had an endothermic reaction, then the conversion as a function of temperature would look like this. And what it tells us is that we won't get any conversion at all for an endothermic reaction. That's one for which the heat of reaction is positive, sucks up heat as the reaction proceeds. though we won't get any conversion at all until we get to a high enough temperature. And the converse is true. If I have an exothermic reaction, that one is disfavored by high temperature. Exothermic reaction is one where the heat of reaction is negative, so heat is given out. And what we have is that we have to stay below a certain temperature range in order to get any reasonable conversion. So I hope everyone is qualitatively okay with this. So let's get specific, and let's go back to our reaction where I'm oxidizing sulfur dioxide to sulfur trioxide. This is the beginning step in making sulfuric acid. And we're asked here to prepare an XT diagram for this reaction at a pressure of 2 bars. I'm just setting the things here with an initial composition with an equimolar amount of SO2, O2, and an inert nitrogen. Again, it's assume ideal gas behavior. So we choose a basis now again such that xi is going to be equal to x, and that's going to be evidently here we've got SO2 is going to be our limiting reactant, and so a stoichiometric number for that is 1 over 1 or just 1, so we take a basis of 1 mole of SO2, and under those conditions x is equal to xi. So I'll make my usual table here, and this should be familiar to you, I hope, where I lay it out in the following way, and write down first in the first row would be the initial number of moles, and in the second row is going to be the equilibrium number of moles, so I write that out in terms of the x's here. Would have been xi's, but now I'm writing it in terms of x, because it's the same thing. And then write out the expression for each of the mole fractions in terms of x, from which I can construct the situation that I'm interested in. So what I've done here first is, I probably should have done it in reverse order, but I evaluated the log of k itself, which I know is going to be of this functional form, and we've seen before how we can construct it out of these reference values that can be put together by knowing what the formation reaction values are for these things. It's important that you be clear about this. Everyone okay with this? So this is sort of a routine thing. So when you do it, it comes out to be in the usual form. You get a constant here, plus or minus some other constant over t. That's what it's always going to look like. But we also have here this, doesn't want to let me write on it without messing around. It has this thing to account for the fact that the pressure is something other than the standard reference pressure of 1 bar. We've got it at 2 bars, so we have to subtract here nu log p. So log ky here is going to be equal to this expression that I've got up here, then minus a half log of p, which is 2 bar. And we put that together, then I've got log ky looks like this. And then I can put log k, the expression for log ky based on my previous stoichiometry table here, and that looks like this. So these log ky's, of course, are the same thing. So if I equate them to one another, I'll get an expression here for the equilibrium conversion temperature diagram. So what I hope you realize at this point is that that's what this is. This is the equation for the equilibrium temperature relationship. In this particular case, as I've assumed that I've got this type of relationship for the dependence of K on temperature, I can actually write it as an explicit expression for temperature. So if we want to prepare this and plot it, then I can set up a spreadsheet. I didn't really need to have KY, I put it in there because it was of interest. What I can go is directly after I assume an array of values for X, for each one I can calculate the value of T, and that's what's given over here. And if I plot that up, it looks like this, which is what we would expect it to look like if it were an exothermic reaction, which this is. So we aren't gonna get any conversion if we get temperature as much above 1,000 degrees or so, okay? Important thing to know. Now, I made the assumption that we can treat the enthalpy of reaction here as constant with temperature, but we had done earlier, I think yesterday, the more detailed analysis for temperature, and if that were the case, then that expression I would have for log Ky would be more complicated. I have this relationship for temperature. And we could make a similar table if I wanted to do that. For each of the values of x, then I would have to find a root for temperature and plot that over here. But what we've seen before is that it would be almost within a line width of what I've got. So I'm not going to do that. So let's look next at the effective pressure on the conversion, because I put it in here at a value of 2 bar, so it would be something different than the 1, but at a given temperature, so again, same reaction. And we'll notice that we have this one-to-one relationship between Ky and x. As x gets bigger, then Ky gets bigger, or vice versa. So we're interested in what the effective pressure is on Ky, and hence that will have the effect on x. So Ky can be written this way. I'm going to then pull that around, and I notice that what's important here is this exponent, which is minus the stoichiometric number for the reaction. Stoichiometric number for the reaction we had here was -1/2, so I got a +1/2 over here. So I notice that if pressure goes up, then the extent of conversion should go up, everything else being equal. And I can write it down here, log Ky for the case of pressure of 2 bar. This term looks like this, 0.3466. And if I let it jump up to 10 bar, then I get a higher value. So if I plot that up, what I notice is the equilibrium conversion curves then reflect this fact that at 10 bar I get a higher conversion than I do at T bar. And this is a consequence of the fact that I get a decrease in the number of moles per mole of reaction, right? I have SO2 plus 1/2 oxygen going to 1 mole of SO3, so there's a decrease in the number of moles, quantitatively 1/2. So if I have a decrease in moles, that's going to favor, higher pressure will favor that because it squeezes it down. So that should be sort of instinctive. Next thing we should look at is the amount of inerts, because we have a number of handles that we can vary here. Temperature, pressure, and another one is the number of inerts that we may have. Now, I had stuck 1 mole of nitrogen in all of those previous calculations, so we did have some inerts present. But let's, for a moment here, consider the situation where I let that float. So I'm having a number of moles of inert here, just Ni. And before that was just 1. And then redo our stoichiometric table, leaving this Ni as indefinite. So if I do that, that's the reaction. And then my expression for Ky looks like this, and you notice it's the same as before, except now I've got Ni here as an explicit term. And if I plot that up, varying the number of moles of inert here, at a pressure of 2 bars, temperature of 1,000 K, what I notice is I start out here with no inerts present at all. I get a conversion of 0.5. But as more and more inerts are present in the system, not surprisingly, the amount of equilibrium conversion goes down, which may or may not be what you might want to happen. But if you want to maximize conversion, then you want to have no inerts present and the reactants in stoichiometric proportions. So we get a max X when we have 0 inerts. And reactants in stoichiometric proportions. Which is perhaps self-evident, but you can show that. So what we've shown is a number of situations here. I've considered variables like temperature, pressure, and now the presence of inerts. And the consequence of all of these for equilibrium conversion can be expressed qualitatively by what's called Le Chatelier's principle. There's more information than you want to know about Le Chatelier's principle, but basically it can be stated verbally as any change in status quo prompts an opposing reaction in the responding system. So if an exothermic reaction, I raise the temperature, that's going to be bad, that'll shut it back. If I have a reaction which increases the number of moles of gas produced per mole of reaction, then that's going to be disfavored by high pressure. And the presence of inerts is going to disfavor conversion in all cases. So let's just take a look at a summary of this. As the temperature goes up for an endothermic reaction, that is one that absorbs heat, the equilibrium conversion will go up. As the temperature goes up for an exothermic reaction, the equilibrium conversion, other things being equal, will go down. So that's one consequence of the so-called Le Chatelier principle. As the pressure goes up, then if the stoichiometric number of the reaction for just the gas phase components here is greater than 0, then the conversion goes down. Whereas if that stoichiometric number for the gas phase components is negative, then an increase in pressure will actually increase the conversion that we achieve. And that was in line with the example that I went through. And then if I have inerts present, they will always decrease the amount of conversion in proportion to the amount that you have, other factors being equal. So that is it for today. Because it kind of goes fast here, unless you have questions or discussion. Yeah.
So if you increase the pressure with an inert, you're increasing the pressure, which would increase the conversion.
Well, you're actually changing two things at the same time then.
Right.
So that's more complicated. You've got to look into it. Yeah. You see, yeah.
Well, when you mentioned the endothermic, or exothermic reaction against lightning not being favorable at higher temperatures, is that because the reverse reaction, which might be endothermic, then becomes possible?
I'm just considering it going in the forward direction.
Okay.
And you look at the reverse direction, that's an interesting question. As a separate issue and then put them together.
I was also curious about the reaction stoichiometric coefficients. We've been getting like a V that's like a sum of
Yeah,
each
it's
of
for a
those.
new, yeah.
Yeah. What I'm curious about is there anything that tells us what, I guess, multiple of that reaction to be dealing with? Because we've had like an example with 1 SO2, 1/2 O2 equals, or goes to 1 SO3, but that could also be described as like 2 SO2, 1 O2.
Oh, I see. If you multiply, everything will come out the same.
Oh, well, okay.
Yeah. The news will then, you just correspondingly increase them, but in proportion.
Okay.
So it's usually best to write the lowest values you can.
Okay.
Yeah.
Sorry, can you reiterate the meaning of the KY versus KT again?
KG?
KY versus KT?
What is KG?
KT.
KT.
Yeah.
Yeah, I put the T there just to indicate that that's the temperature at which we want Ka. So the K I'm talking about there is the one in terms of activities, which would otherwise not have a subscript at all.
Okay.
So I could write, there's so much notation here. I could write K parentheses sub T.
Okay. Is KY just the?
That's K, you know what K is, that's a continued product of the quantities raised to the stoichiometric coefficient powers. So I could write that in terms of Y, I could write it in terms of partial pressures, leading to what's called a KP value. I don't see the value of that, so I didn't do that, but people have done it. Well, we've seen it written out for the fugacity coefficients, for activity coefficients, everything, but it's that continued product of the entities raised to the stoichiometric coefficient powers.
Thank you.
Yeah. Yeah,
If you wanted to look at the reaction between two molecules that are large or otherwise not their heat of formation is not documented, and you just wanted to look at the reaction
the heat reaction is not what?
documented for like
Not documented.
right? You can't find it in a table or anything. They're large or unusual molecules. Could you look at the heat of reaction between just the functional groups and get a fairly accurate?
That can be done.
Yeah.
We're not doing that, but
Okay.
that actually can be done, and actually they can do very well with it.
Cool.
Yeah. Anything else, or are we finished for the day? This runs too fast when I've got it all in PowerPoint, so it's up to you to slow me down. If not, then we're done for the day, and I will see you then tomorrow.